let's get started. So we're getting pretty close to the end of the semester, actually. We have like less than a month left. So today we'll be finishing up all the information for the second part of the CoGen project, how to compile branching statements from simple IR to assembly. And then we'll finish up the compiler stuff with pointers. Before we begin, questions about the projects, questions about homework, questions about logistics, questions about last time. So I think I showed you this last time. This is CoGen 2. So it's very similar to CoGen 1, except I've given you a whole bunch more functions. I've given you function implementations for CoGen 1, but they're hard-coded assembly for one particular simple IR file, for this simple IR file. So if you follow the directions here to hard-code the assembly in these 5 functions, you'll generate the assembly code for this IR function. And if you implement your own versions of these 4 functions, the arithmetic operations and branching, then any other code you add inside of this IR file will get generated by those functions you implemented for the project. Any questions about that aspect? Okay. All right, so yeah, let me know if you have questions about that, ask about that stem. You always have to keep in mind what the compiler is doing. The compiler is generating code, and it's generating assembly code. And then you can just use the rest of the Unix C toolchain to compile that. Yeah?
So the tester for the project is just like compiling it and making sure the output matches, right?
It's compiling it and running it. It runs it.
No, sorry, I meant it's using the compiler to compile stuff, and then so
Yeah.
I mean, I'm not going to actually do this, but could you just convert the simple IR to C, since it's pretty easy to map that to C, and then you call GCC to convert that to assembly?
I mean, if you feel comfortable doing that to make it, you mean easier than doing assembly?
Yeah.
I would say yes, you could do that. I mean, I'm not saying you should. I guess technically that would be not following the project.
Yeah.
But if you're comfortable enough with code generation to do that, I would consider that I've succeeded in teaching you code generation.
It's like significantly easier than doing it to assembly, because you don't really have to think about anything. Each of the lines pretty much directly match to the line of C.
That's true. Yeah, that's true. Yeah, you could do that. Yeah, yeah, yeah. That would be a way around it. But if you're still doing that, you're still at least understanding the concept of code generation. So don't do that, I guess. Do the assembly. Yeah. Yeah, the assembly.
But I was just thinking it would theoretically be a way.
Yeah, for sure. And since we're testing the output, although I didn't give you enough, this is why I hide some of the test cases. You could also just write code that would write out just something that prints out that answer, right? Because I just run the code. I don't check whether the code works, actually matches exactly the input code. Yeah. So you could just say print 5 or something,
You could also make it output malicious code.
That's true. That's why I don't run on my own machine, this stuff. So absolutely, I mean any coding project, you could put malicious code. Somebody actually found a misconfiguration of Eustace last semester where you could access other people's files. It's not supposed to happen. But yeah, it was a good catch. I had worried about that as well, so I don't even put I try not to put even answers on Eustace because it's a shared system. So, but if you're that sophisticated, so one semester I told people I used to give the compiled version of the compiler so you could compare against it, and I told them, look, you could just disassemble it and use a decompiler. And I was like, look, if you can do that, just show me because that's cool if you actually do that. So some kids actually did it. Yeah, they used Gidra, exactly. It was the year Gidra came out, and they used it. And I had done a lot of it was in C, so I did a lot of struct heavy stuff, and it actually couldn't reverse the types well enough. But for all the function calls, it could work. So I don't give out the binary anymore of the compiler. But yeah, if you can do all those sophisticated things, let me know. That could be a bonus project. If you can do that. I want you to learn. So if you have those chops and you develop those chops and you want to try it out, by all means, try it out. It could be like a bonus project. But sure, yeah, simple IR and C are very close, or at least it's a subset, as you observe. Right, yeah. We'll talk about that a little today, like how do you do loops and stuff like that. Yeah, for sure. So it's a superset of the language. Other questions on the project? Okay, let's go into the homework from last time, which I completely forget. Let's see what it was. There it is. It was about division and remainder. Okay. So this was just to remind you of the idiosyncrasies of the Intel x86 64 architectures, or I should say AMD 64. AMD actually developed the 64-bit architecture, so I should make sure I give them credit. AMD 64, their integer division operation, it only takes a single argument. So other arithmetic operations, add, subtract, integer multiply, they all take 2 arguments. So why does integer division only take 1 argument? And how do you set the other argument? The other one is in which register? So the other one is in a fixed register. It's like the other one is in a register, but it's only in one fixed register. It's in RAX, actually RDX and RAX. But it's just because the integer division operation has to use specific registers to work. So the other arithmetic operations, you can give it any 2 registers. Division, you have to use a specific register, and that's RAX. And you use CDQ to extend it into RDX. All right, any questions on that one? So that was just to remind you that most of the arithmetic operations are going to be really similar. So when you write the code generation for it, it'll be a very simple template. I basically showed you the template last time. You just generate the loads from variables, generate the corresponding assembly instruction, and then generate the store for the left-hand side of the arithmetic instruction. And add, subtract, multiply, those are going to be exactly the same, except you change the mnemonic. Add, sub, imul. Those are all going to be, the code is going to be otherwise the same. But for division, it's a little different because you have to use CDQ for sign extend, and you have to use a single operand. But otherwise, it's all a very simple template, very similar template. All right, questions on the homework? Questions on anything about arithmetic? So hopefully, I think arithmetic is probably a simpler part of the compiler. I don't want to say simple, but simpler part compared to the function generation, because you've got to know the calling convention, and pointers, because pointers are just confusing. Branching is, I think, kind of the second most simple part. That's what we're going to cover today. But it's a little tricky. There are some sort of gotchas when trying to do generation of branching code. All right, other questions before we go on to today's lecture? Okay, let's do branching code. All right, so the goal of this, just like your classmate observed, this looks very much like C. So if you ever use goto in C, works very similarly in assembly, at least for unconditional gotos. So our goal is to take simple IR, which has labels and unconditional gotos, and translate them to assembly. So in the AMD 64, and actually Intel 32, they're called jumps instead of branches. And the mnemonic in assembly is JMP, jump. And the assemblers also support labels. So for unconditional branches, the code's very similar between simple IR and assembly. So that's the overall goal. And just like assemblers, simple IR supports labels. Do you see these in MIPS, in computer organization? You saw labels? It's okay. So labels are just named locations in the code. So if you remember from computer organization, how is code stored in the machine? How does this program get stored in the machine while it's running? Or where is it stored while the program's running? Yeah, in the memory. In memory, so in RAM. That's the way most machines work. The data, the code itself is stored in memory. And how are locations in the code represented in the machine? Or how could you say, give me, what's that? An address, yeah. So it's just RAM, just like you access data, at least in this model, this von Neumann machine model. Did you guys learn about von Neumann versus Harvard architecture? Harvard, there's two different storage locations for the code and data. Von Neumann architecture, the code and the data are stored in the same RAM. So some examples of, say, I think it was the Harvard architecture, some of your phones may have a ROM chip, or some older Apple devices, like the original Mac, had a ROM chip. And that's kind of closer to not really a von Neumann architecture, because the code is not in writable, the code is not data in that architecture. What's that? Or a video game cartridge, yeah, a video game cartridge, yeah. You can think of that as more like not really a von Neumann architecture, although, yeah, right, yeah, I think it actually does read from there. But in the architecture we're using, code is data. So code is stored just like data is stored. It's stored in the same memory space. And in fact, you could write code that, without any other protections, you could write code that's self-modifying. You could write code that will change the code that would after it was loaded. A lot of malicious code does this to try to avoid detection. So okay, just a little review of computer architecture. Okay, so if each line of assembly, each instruction of assembly is just data, it's just converted to machine code and then stored in RAM as data, and at the addresses, just like for code, or just like for data, the addresses correspond to code. What address does this label translate to in assembly? Well, you don't know, right? You can't know, or you won't necessarily know at assembly time. So this is what the assembler and the linker do, and the loader. They set up the address, and this just makes programming easier. You don't have to know ahead of time what the addresses are, and you don't have to compute where the jump goes to. So when you branch to a label like this, I branch to the loop instruction, this gets converted to a relative offset from the jump instruction. So this is what the assembler will do for you. The assembler will figure out where this loop is in your code, take the difference of where the program counter locations will be, or the address locations, and fill that in for you. So to make this easier, Simple IR also supports these kind of labels. You don't have to do your own address calculations. But just, this is just a little review of computer organization. So just to remind you that these labels correspond to memory addresses. And it's the assembler, linker, and loader that will make these labels actually real addresses in memory. All right, questions on this? Questions on kind of the basics of branching from the architecture point of view? Okay, hopefully that's a review. All right, so let's take a C-like language like this. How can we represent this in machine code? Or let's use Simple IR. So Simple IR is close to machine code. How could we write this kind of C-like conditional statement in Simple IR? Remember, Simple IR does not have if statements. What does it have? What branching instructions does it have? If goto. It has goto and it has if goto. So let's see if we can work out how to represent this in. All right, so what would the Simple IR look like for this? Let's assume we already have a function. What might the Simple IR look for this? So x equals 11. How could we write that in Simple IR? Yeah, x equals 11, right? Using the different syntax, right? So that's how you would translate that. And x plus 1 equals 1. How could they translate that into Simple IR? Yeah. Pretty straightforward, right? So you're already learning a little bit about the front end part of the compiler, how you desugar a language from one syntax to another. All right, what about the branching behavior? How can we represent or simulate this kind of if statement semantics using simple IR? Yeah, go ahead.
Like, put a label after the x equals 11, and then jump to it if x is not less than that.
Okay, so let's call this the, not if, or let's call this the end of the if statement, right? So we put a label here, and somehow we want to branch to that. Branch if x greater than 10 is not true, right? So if it's true, we don't want to branch, right? Okay, so what instruction in simple IR has this kind of semantics where we branch only if something is true or not true? If go to, right? So we say if some condition, branch to the end. So this is the body of the if statement in here. And so we want to branch if it's not true, right? So if it is true, we don't want to branch. So what condition do we put here to only branch if it's not true? Yeah, it's the negation of this, which is x less than or equal to 10. So if you ever do any, some people might go into security or want to do kind of low-level system stuff. When you look at compiled code, typically this condition gets inverted because we want to enter the if statement when it's true. So that means we don't want to branch if it's true. And so that's why you'll see most compilers will invert the condition to generate a conditional branch. Okay, so we have x less than or equal to 10. Go to end. All right, are we done? Is this going to give us the same code? Let's run it. So let's say x was 12. Or actually, let's say x is 9. Let's say x is 9. Let's run each line of this code. So okay, so is this condition met? Is 9 less than or equal to 10?
Yes.
So I think this condition's met. We branch here, and now x equals 10 here. What about in the original C program? If x was 9, what's the result of x going to be at the end of this program? 10. So it looks like it's the same, right? Let's try x equals 12. So is this condition met? No. So we go to the next line. Now x is 11. And what's the next line that gets executed here? This line. So we get x equals 13, right? Looks good, right? Looks good. All right, let's take another example. Oops. Let's make this increment the else branch of this code. So what would the simple IR look like in this case? So we have something similar here, right? We say x less than or equal to 10 because we don't want to branch if it's true. Let's do it over here. Go to end, or go to if branch. And we'll probably have something similar here, right? Where we okay, is this program the same? Is this simple IR program the same as this C program? Here's some head shaking no. Why not? Yeah, x equals x is always being executed. So if x, so just to show you why this is the case, if x were 12, then this should execute, and x should be 11 at this point. But in this program, if x is 12, then it's not less than this, so we branch here, and x become, oh wait, I have this mixed up. Sorry, if x is 9, all right, I'm confusing myself. If x is 12, oh yeah, right. So x is 12, it's not less than this. Where am I getting confused? X is 12, it's greater than 11, so it becomes 11. Oh yeah, right, it's not less than, sorry, bad at math. So 12 is not less than this, so we don't branch, it becomes 11, and then we do x plus 1, and x becomes 12. So we get a different answer for the two programs. So what needed to change for an if-then-else block? Yeah, add a unconditional go-to statement here to skip past the else branch. So now when we run this program, if x is 12, becomes 11 here, and then we branch unconditionally here. So this gives us 11, as expected. All right, questions on this? So I just want to show you a little bit of how, so you won't have to write a compiler that does this. We're going to give you simple IR. But I just want you to be a little bit familiar with what the kind of patterns in assembly or IR look like after they get compiled from a C-like language. So you won't have to do this compilation. You can do it as a bonus project if you like, or take compiler construction and we'll do this. But I just want to show you, the kind of semantics of conditional branches, how they work in assembly. Yeah. Switch case statements. So in C, they're typically compiled to a table, which may seem counterintuitive. So you could treat a switch statement as just a series of if-then-else statements. You could treat them as equivalent to something like this. The problem is these break statements, if the break statement is not here, then you have fall through from this. So how these are typically compiled is each line of code here is given an address or a label, and then there's a table constructed with all of the addresses of the cases, and then the switch statement is just a lookup to that table and then a branch to that instruction. That will allow the fall through to occur. It's also more efficient than branching because you don't have to test each case. You can test it once. Don't worry about that too much. That's a really good question, how switch statements are implemented. It doesn't have to be this way. You could also try to implement it this way and use go-tos for the fall through behavior. But I think for efficiency, most compilers, will translate this to a table, a lookup table, and then index into it. Because in C, these cases, they have to be integer constants, basically. They have to be integer constants. So they have to be computable at compile time for this optimization. But yeah, it's a good question. Okay, so we can go over some more translations of how the simple IR will be created, how assembly programmers will implement C-like semantics. But you don't actually have to do that. You don't actually have to do this translation. I just want you to be aware of this because when you do testing, I think it'll help you if you know how to do this translation by hand. Okay, so that's how C-like conditionals can get represented in IR or assembly. And yeah, we have an example here of just like what we saw. It's like the same thing. Okay, just as a refresher, how do we, when we're translating this to assembly, how do we access X's data? It's kind of a refresher from a couple weeks ago. How do we access X's data? Where does X's data live if it's a local variable in simple IR. Yeah, offset from RBP. It's offset from the stack. So just to refresh your memory, we would translate X into something like this, where we have RBP, the pointer to the stack frame, and then we have an offset into the local variable space into the stack frame. Okay. All right, so here's the Intel, or the AMD or Intel instruction for doing comparisons. So this is how we're going to actually implement an if goto. So unconditional gotos are really easy. They're just the jump instruction. For a conditional goto or conditional branch in the x86 world, we have to do it in two steps. So we first use a compare instruction, which is going to take two arguments. So it's going to compare RAX to RBX. Remember, the arguments are flipped. And then what's kind of idiosyncratic about the x86 architecture is that then we have a whole series of different instructions to branch on each kind of condition that we'd like to branch on. So JLE says jump if the result of the previous comparison was less than. So let me show you what this looks like with a full example. So if we're trying to translate if x less than or equal to 10, go to false label, this is what the assembly code might look like for that. So first we need to be able to get these values into registers. I mean, you can do immediates and you can do loads, but for simplicity, I just get everything into a register. So if you've loaded RAX into X into RAX and loaded 10 into RBX, this is the comparison. So remember, they're flipped. So RAX has the value of X and RBX has the value of 10. So first we do a compare, and then immediately after we do this jump less than or equal. So the reason for this is in the x86 world, after the compare instruction, and actually after every instruction that does arithmetic, there's a hidden flag register that you cannot directly access that stores whether the result of the last instruction was 0 or whether less than 0. And these branch instructions will inspect that register and perform the branch if the condition is true, if the less than condition is true. So just a kind of idiosyncrasy of assembly. These are all of the conditional branch instructions that we're going to use from x86. I think there are others, but these are the ones we're going to use. So jump if equal. This corresponds to the simple IR operator equals. Jump if not equal, NE. That corresponds to simple IR not equal. L is less than, LE is less than or equal. G is greater than, GE is greater than or equal. So this table already kind of shows you a compilation strategy. You can just look up this operator symbol and translate it to this assembly operation mnemonic. If that kind of makes sense. So this is like a translation table from simple IR to assembly. All right, questions on this? So this is just one way we can implement branching in assembly. This is an easy way, I think, the easiest way to translate this simple IR to this assembly. Yeah?
The compare instruction basically just does the subtraction. It doesn't store the result, right?
That's exactly right. That is exactly the semantics of compare. It's a subtraction of RAX minus RBX, but yeah, it does not store the result in RAX. So if you did the subtraction, it would set the flags, the register flag, the flag register in the exact same way, except RAX state would be changed. But yeah, that's exactly it. So it's a subtraction instruction. So why this is the case is if we've got compare 10, 12. Actually, I think I have a link to the compare instruction here. Oops, that's not what I meant to do. Maybe it's in, oh, here it is. E flags register. So the flags register stores whether the result was 0, whether it was negative. And it turns out that if you know whether something was less than or whether something was 0, you can implement greater than, you can implement equals. So for instance, if I knew whether a subtraction resulted in 0, how could I implement equals from that? So let's say I'm subtracting, I know that a minus b equals 0. How do I convert this into a test for equality? This hopefully is like high school algebra to do this. How can you convert this into a test for equality between A and B? Yeah. They're equal. Yeah, well, the sort of algebra proof is that you can add B to both sides, right? I mean, I know maybe this seems too obvious, but you probably all sort of learned this already. But this is like a proof that A minus B equals 0 implies that A equals B. So let's try a trickier one. So let's say I know that, let's say I want to prove that A is greater than or equal to B. If I only have equals and less than, how could I prove this with only these two operations? If I only had these two operations, how could I prove that A is greater than or equal to B? What's that? If B is less than or equal to A, so it's B is less than an A. But B is less than A. So if B is less than A, that implies that A is greater than or equal to B, right? Or no, B is. I'm confusing myself here. This is why I probably shouldn't do this on the fly. Let's see. Let's go the other way. So this implies that. Oh yeah, you're right. B is less than or equal to. Oh, sorry. I forgot to give you an operation. You also have not. You also have negation. So you can negate as well. Let's say you negate as well. Then not this implies B or A less than B. So yeah, you're right. So if you had greater than, if we had B greater than or equal to A, then that would imply that A is less than or equal to B. But then you don't have the less than operation. So you need a way to use less than, and the way you do it is with negation. So negate it. Anyway, this is more for compilers class. I hadn't prepared for this. It's a little twiddly how you do this for each case. But this is how the architects, I guess, they save on circuitry. So they only support equals and less than. And you can see there's only flags for these two cases. But from those, you can implement greater than or equal to, less than or equal to, greater than, and not equal to as well. You can implement all of those. So I guess incidentally, how would you implement not? Well, you just do a branch. So if you can branch on A less than B, or you can branch on B less than A, then that's equivalent to branching on A greater than or equal to B. Not branching on A greater than or equal to B, if you get my point. So if this is my if branch here, then I just put my else branch here and my if branch at the label. Anyway, this is a little outside the scope of what I want to address. But yeah, so this is what the flags register does when you use the compare instruction. It's like a subtraction. So if you subtract two values that are equal, the 0 flag will be set. If you subtract between where the first operand is less than the second operand, then the negative, what do they call it? The sign flag will be set. The negative flag will be set. And if you Do it this way, you get no flag set. If you have greater than, the first operand is greater than the last one. And so that's all you get at the architectural level. But from this, the architecture will give you all of these options, all of these conditional branch instructions. It'll construct all of these from these two flags, the existence of these two flags. Anyway, this is more for computer architecture or compilers. But yeah, that's how compare is implemented. It's just a subtraction that sets these 0 or sign flags. Okay, but you don't actually have to know how this is implemented. It's enough to just remember that you have a compare instruction, and then immediately after the compare, you pick the corresponding assembly branch instruction, conditional branch instruction, corresponding to the simple IR operation you'd like to have. All right, questions on that so far? All right, so this is the pattern for converting a simple IR conditional branch into assembly. So here we've got our operand, our operator, and our second operand, and then our label. And everything in capitals here, this is what can change in simple IR programs. So if and go to are keywords, but if you look at the grammar, these can have different options. So operand 1 can be a name, or I think a number. Operand 2 can be a name or a number. Operator is one of the 5 operator syntax, and label can be any name in the language. So the template for conditional branching is this. You take whatever operand 1 is, and you convert it to assembly. This is going to be the offset from the base pointer. Store it into a register. So I have it, my compiler always uses RAX for the first operand. Take the second operand, always store it in RBX. Then do a comparison between RAX and RBX. And pick whatever the corresponding operator label is for jump, and print out that jump to the label. Questions on this? Questions on this template? Pretty straightforward, right? It's even simpler than the arithmetic, I think, the arithmetic instructions, because there's only one template for generating this. And you just translate the operands and the operators and plug them in to this template. Okay, so let's do a complete example. All right, here's our if x is less than or equal to 10, go to false label. If we don't branch, then we set x to 11. If we do branch, then we set x to x equals x plus 1. So here's the translation of x, this if go to, x less than or equal to 10, go to false label. So the first thing we do is get the operands. So assuming that you already have the symbol table. Remember, the symbol table is given to you in the compiler, so you just do a lookup into the symbol table. And we take the first operand and copy it to RAX. We take the second operand, translate it to assembly, and copy it to RBX. Questions on that? So just like with arithmetic, we copy the operands. Yeah? Yeah, absolutely, yeah. Symbol tables used, every compiler will have a symbol table that will store offsets. It's also used for type checking and also program analysis. So you can use a symbol table to keep track of what variable values will be at runtime and use that to do bug finding. Take a program analysis or compiler construction to see how that works. But yeah, symbol table is a common technique. Symbol table and parse tree, those are the core data structures for the compiler front end and back end for the symbol table. Okay, so we get the operands just like with arithmetic. We issue the compare instruction. We always do that for every type of condition we have. And then we pick the corresponding branch, the conditional jump instruction corresponding to our operator. And just as a refresher, here's assigning x to 11. So in my compiler, I always set RAX to be whatever value I'm going to store, and then issue the store instruction to whatever the offset to x is. Questions about this? This is hopefully a review. And then false label, how do we translate a label to assembly? It's exactly the same. Yeah, you just print out the exact same syntax. It's just the name of the label. And then x equals x plus 1. This is hopefully, again, review. So just to refresh you how this works, we first load the operands into registers. So we take whatever x is, load it into RAX, take the immediate value 1, load it into RBX. Then we take whatever the operator is, and we convert it into the assembly version of that operation and issue the addition. And then we store whatever the result is, which is an RAX now, because remember the destination's on the right, and store that back into whatever the variable, the offset corresponding to the left-hand side variable. Questions on that? Questions on any of this translation? So this is like one example of CoGen 2. So this is doing both branching and arithmetic in one example. And that's it for branching. Questions on branching? Okay, let's take another. So this is not something your compiler will have to implement, but to show you a little bit more about how compilers operate. Let's say instead of an if statement, we have a while loop. So let's take this program here. So what's this program implement in if this is C? What's this program implementing? Yeah. Powers of 3. Yeah, good. Powers of 3. Why powers of 3? I'm multiplying by 3 x times. That's what power of 3 is, right? So if I have 3 to the x, that's equivalent to 3 times 3 times 3 x times. So this is how you can implement one way to implement exponentiation of 3. So how might we write this program in simple IR? Let's start with the assignments, because they're pretty easy to translate. So how do we translate x minus minus into simple IR? X equals x minus 1. That's the meaning of x minus minus. What about result times equals? Yeah. All right, so so how do we translate while into a language where we don't have while statements? We only have conditional and unconditional branching. What's that? Call back to a function. So use recursion. Well, so assembly doesn't really have recursion either, right? I mean, yeah, we could rewrite this as a recursive example, but assume I don't have any function call here. I just have I'm running on the bare metal, and I haven't even implemented functions yet. Well, what are functions? What do functions do? Oh, yeah. Yeah, go ahead,
You should have a label, and then inside the label, a go-to statement, and if go-to statement, that's the label.
Okay, so say again, so where's the first label go? After result equals 1. So I have a label here. Let's say it's the body of the while loop. Okay, and then what's our condition look like? Yeah. Okay, so you're saying put an if here. So if we put the if here, all right, well, okay. Let me show you 2 versions. So to motivate this, let's convert this to C using only if statements and go-tos. So how can we rewrite a while loop into an if statement? So this if x less than or equal to 0, this is close, right? This is close to the same program. If I just convert this to if, what's the difference between these two programs? Or what's result going to be here? If x is, if x is 10, let's say, for all of these cases. Yeah, it's just going to be 3, right? So let's say x is 4. Then at the bottom of this loop, x is going to be, what, 81, I think? If x is 4, result is going to be 3. Sorry, it's not x, it's going to be result. So how can I simulate this while loop using a C program with just an if statement? Yeah, go ahead.
We'll put a label before the if, and then go to that after the...
Yeah, exactly. So this is combining what your colleague just said with an if statement. So this is how you can implement a while loop in C with just using if statements and branching. See? So this is called desugaring, where you take one language that has more language features, more syntax, and turning it into a language that has fewer features. So here, if we had C without while loops, as long as we had unconditional goto, we'd be okay. We could implement the same program in that language. Yeah?
So if you were writing a decompiler, you could have it just the while is when you compile something like that, and you could have it just write something like that, but you probably want to be able to detect that and say this is going to be a while loop, and instead of writing it like that, you can just write a while.
That's exactly right. You can decompile this way as well. So if you know how the compiler generates branching code, you can actually discover what then this is how decompilers actually work. And we actually have a lot of time, so I can actually I'll show that. I'll show what that looks like. I think I have time to actually show what that looks like, since I think that is hopefully an interesting topic for some, how decompilation works. But okay, so hopefully you believe this, that if I take a while loop, I could rewrite that in C without a while loop, just using an if statement plus an unconditional goto. So result is 1. We enter this condition here. It's if x is greater than 4, then we enter this loop. And the first time result is going to be 3. We branch here. X is 2 now, etc. And so result is now going to be 81. Questions on that? Questions on how these two programs are equivalent? So now we've turned this into a program where we have no while loop. So we can either convert this right into a simple IR because we know how to convert the simple IR, or you could even convert this into a C program that doesn't use an if block, where we just use if statements. And it's going to look exactly like simple IR, as your fellow student kind of recognized at the beginning of this class. So the way that would look is we replace this if statement with our our inverted condition. So we invert this condition and do an unconditional go to the end. And so this program here, where we only enter the body if x is greater than 0, here we skip the body if x is the opposite. Questions on this conversion? This is exactly what we did for simple IR. We just inverted the condition and then branch past the body whenever that condition is, sorry, the opposite of that condition is true. Excuse me. Questions on this conversion? Then to convert this to simple IR is very straightforward. This program is almost exactly simple IR already. We just have to do some syntactic changes. So questions on this conversion? How this C program and this simple IR program are the same? Yeah. Oh yeah, sorry, x minus 1. Yeah. Questions on this conversion between this original C program here? So this is C, because C has goto. You can use only a small subset of C, just if conditional statements and go-tos. And you can do the same thing that simple IR does. Questions on that? And then turning this into assembly is what we just saw. We just saw the conversion into assembly here of a program like that. All right. Let's take so questions about translating arithmetic or branching. Questions about the project. Questions about the test cases. All the test cases are now released. Questions about this? All right. So let's do the same exercise for, we've got a while loop example, we've got an if statement example. Let's take one more. Let's do a if then else statement. Again, but we'll just convert it to C. Okay, so how can we convert this program into one that doesn't use blocks but uses go-tos? So we take out these blocks here, and we just have an if statement, and we can do go-tos. So how do we convert this program into if statements with go-tos?
You put a label after x equals 2, and that label is basically your kind of like the condition matches. So you put a go-to statement before the x equals 2 and after the x equals 1. So go-to and after x equals 1 matches.
Right, so it'll look something like this. So we've got a label for else branch, we've got a label for the end of the if statement, and if the condition is not true, so I'll write it like this, if the condition is not true, then we branch to the else branch. So these two programs are equivalent, right? So if this is not true, run the else branch. If it is true, run the if branch and then skip the else branch. Questions on this? Questions on this code? So this is like exactly what our simple IR program looked like. So let's take a look how we can, let's represent this graphically. So let's treat each one of these blocks as a node on a graph, and each one of these branches as an edge on the graph. So let me show you what this looks like. So we've got one node here to start this, which will run the comparison. We've got some code that will, do the computation of the comparison. So let me give some line numbers here to make this a little easier to follow. So line 1 computes x less than or equal to 10 and negates it. And so what are the locations in this program that we can go to from line 1? How many different locations can we branch to, or can we go to next from line 1? We could either go to line 2. So we could go to line 2. Where else can we go? Line 4. So if we represent those possible branches as edges in a graph, then this is what this graph will start looking like. So line 2 computes x equals 1, and line 4 computes x equals 2. What about x equals 2, line 2? What's the next instruction that it goes to? It goes to line 3, right? It goes to this go to branch. And what line does that go to? Line 6, right? So line 6 is going to be some whatever follows the if statement. What about the else branch? We go to line 5, and then what's the next line we go to after the else branch? Line 6, right? Goes to the same place. Both branches end up in the same place. So if you use this scheme where nodes are lines of code. There's the lines of code in your program, and edges show the branches, what the next instruction is in the branches. Then you can diagram in a graph the flow of control in this program. And notice that when you have an if-then-else statement, we get this characteristic diamond shape, where there's some computation in the first node, and then there's a branch to two different the if and else branch, and then both of these branches converge on the same instruction. So this is what an if statement. This is what an if statement looks like. What about our while loop? Let's take our while loop here. Or actually, maybe it's easier to look at our converted version. So this is what our while loop looked like. We branch to the end of the loop if our condition doesn't hold anymore. Oops. We branch to the end of the loop if our condition doesn't hold anymore. If it does, we enter the body and then branch back to the head. Remember this? Questions on this? This is the while loop. So let's do the same exercise where we draw out a diagram for this while loop. So we've got result equals 1. And then we've got a block here that computes x less than or equal to 0. Where does x less than or equal to 0 go? Well, it can either go to a block where we have x minus minus and result times equals 3, or it can go to the end. Right? Following me so far? So this block corresponds to this line of code. This block corresponds to the computation of the condition. And this block corresponds to the body of the loop. And this block corresponds to the other branch that we can go, the end label. What about this go-to head? This go-to head is a branch back to here, the computation of x less than or equal to 0. So this is what a while loop looks like if we diagram this using a graph. It has a single body. It's kind of like an if statement, but it has a single body that has a back edge to the top of the loop. Question so far? Does that kind of make sense? So we have these two shapes of a graph. So let's say we had this graph. Let's say I gave you a graph that looks something like this. Just as a quick quiz, I know I'm putting you on the spot, but what programming language constructs do you think would have made this control flow graph? Good, a condition inside of a loop. So if we box in this condition, then we get the shape of a while loop. This is the shape we get. We get the exact same shape of a while loop. So this, if we just encapsulate this if statement, we turn it into this. And what shape is this? This is a while loop. So what decompilers do is they take these arbitrarily complex graphs that represent control flow. So I might have something even more complicated, like this. And this looks even more complicated, right? So anyone figure out what this is? It's several nested things. So here's how decompilers work. They take these three patterns that you have for if statements, while loops, and if-then-else statements, and they match them in the graph. So here we have the pattern of a while loop. So it finds the smallest pattern that it can. and it replaces it with just the code for a while loop. So whatever the condition is, going to be some condition, and it replaces it with the code for a while loop. So this is while 1. So let's say this is while loop 1. And now it tries to continue its matching. So it sees that there's a match here for an if-then-else statement, right? This is the diamond shape of an if-then-else statement. If we replace this while loop with a single block, we get the characteristic diamond shape of an if-then-else statement. Color that in, and now we get an if statement. And we can generate code around this if statement for an if-then-else statement. And because it was inside the while loop, we know that it's nested. We know that this while loop is nested inside of this if statement. So here's our if statement that we discovered. And then finally, we have the characteristic shape of a while loop again. So this whole shape here, this is the shape of a while loop. And so we know that this if statement, which had a while loop listed inside, is inside of a while loop. So this is our outer while loop. And this is how decompilation works. So if we make this graph out of the just branching behavior of the program, and we draw it as a graph, we can identify the characteristic patterns of control flow statements and incrementally replace them in our graph to discover all of the nesting behavior of our original program. So I'm not going to test you on this. You're not going to have to implement this. But this is what decompilers do. This is how they work. This is how they go from assembly code, which was which is a smaller language, and infer what the larger language was from the assembly code. So decompilers like Ghidra or IDA-Pro, this is how they do it. All right, questions on that? So you can see we've backed out the nested behavior of this program, a nested behavior of this original program. Now there are ways to obfuscate this. There are ways to hide this. Optimizations may get in the way. But yeah, so if anyone wants to do a bonus project, let me know. You can do this. It's really not that bad. It's not too bad. Questions on this? All right, so this is a little, yeah, go ahead. Yeah, my compilers class will teach that. So this is just drawn from my compilers class. So we'll show how to do this analysis of the assembly or IR code to find this graph. So it's a classic called control flow analysis, a classic analysis of binary code or machine or IR code. Yeah. What's that? Yeah, everyone implements a full compiler. Yeah, we do a lot in optimizations and analysis. So the kind of stuff that allow you to discover this structure of code is the kind of analysis that we'll look at. There's been decades of research in the compiler community developing these kinds of analysis, originally for optimization, but these have more recently been used for security analysis. So you can use the kind of analysis, automatic analysis techniques in the compiler to do things like find null pointer errors, find control flow, do decompilation, find security vulnerabilities using these compiler techniques. And there's also testing techniques and combinations of these. So testing like fuzz testing, you've ever heard of fuzz testing? That's a big area of research that runs the program to find bugs automatically. But all right, so this is a little extracurricular. This is I'm not going to test you on this, but just to show you, since some people were asking about decompilation, yeah, if you can see these patterns in the control flow graph, then you can actually back out, you can infer what programming language constructs were used for this. So it's not the only issue. There's a lot of other issues in decompilation, figuring out types, variable names. Variable names you may never be able to recover, but at least you can start to make the code look like the original source code. All right, so other questions? That's all I have for today. So ended a little early, branching went fast. And have a good one. See you Wednesday.